is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Just to give an overview in 3 lines, the text is the book of that name, Computational Science and Engineering, that was completed just last year. So it really ties pretty well with the course. I don't cover everything in the book, by all means. And I certainly don't stand here and read the book. That would be no good. But you'll be able, if you miss a class, well, don't miss a class. But if you miss a class, you'll be able probably to see roughly what we did. Okay, so the first part of the semester is this applied linear algebra. And I don't know how many of you have had a linear algebra course, and that's why I thought I would start with a quick review, and you'll catch on. I want matrices to come to life, actually. You know, instead of just being a 4x4 array of numbers, they're a 4x4 or n by n or m by n array of special numbers. They have a meaning. When they multiply a vector, they do something. And so it's part of this first step is just like getting to recognize what's that matrix doing? Where does it come from? What are its properties? So that's a theme at the start. Then differential equations, like Laplace's equation, are beautiful examples. So here we get especially to numerical methods, finite differences, finite elements above all. So I think in this class you'll really see how finite elements work and other ideas, all sorts of ideas. And then the last part of the course is about Fourier. That's Fourier series that you may have seen and Fourier integrals, but also highly important discrete Fourier transform, DFT. That's a fundamental step for understanding what a signal contains. Yeah, so that's great stuff, Fourier. Okay. What else should I say before I start? I said this was my favorite course, and maybe I elaborate a little. Well, I think what I want to say is that I really feel my life is here to teach you and not to grade you. I'm not going to spend the semester worrying about grades, and please don't. They come out fine. We've got lots to learn, and I'll do my very best to explain it clearly. And I know you'll do your best. I know from experience this class goes for it and does it right. So I'm just, that's what makes it so good. Okay. Homeworks, by the way, well, the first homework will simply be a way to get a grade list, a list of everybody taking the course. They won't be graded in great detail. Too large a class, and you're allowed to talk to each other about homework. So homework is not an exam at all. So let me leave any discussion of exams and grades for the future. I'll tell you, you'll see how informally the first homework will be, and I hope it'll go up on the website. The first homework, it'll be for Monday, so it's a bit early. But it's pretty open-ended. If you could take 3 problems from 1.1, the first section of the book, any 3, and any 3 problems from 1.2, and print your name on the homework, because we're going to use that to create the grade list, I'll be completely happy. Oh, especially if you get them right and do them neatly and so on. But we won't know. So that's for Monday. Okay, and we'll talk more about, I'll announce the TA and on the website, the TA hours and the office hours and everything. There'll be a Friday afternoon office hour. So, because homeworks will typically come Monday. Okay, questions about the course before I just start? Okay, there's time, another time for questions too. Okay, so can we just start with that matrix? And so I said about matrices, I'm interested in their properties, like I'm going to ask you about that. And then I'm interested in their meaning. Where do they come from? You know, why that matrix instead of some other? And then the numerical part is, how do we deal with them? How do we solve a linear system with that coefficient matrix? What can we say about the solution? So that the purpose, right? Okay, how about, well, now, help me out. So I guess my plan with the videotaping is, whatever you say, I'll repeat. So say it as clearly as possible, and it's fantastic to have discussion, conversation here. So I'll just repeat it so that it safely gets on the tape. So tell me its properties. Tell me the first property that you notice about that matrix. Symmetric. Symmetric, right. I could have slowed down a little and everybody probably would have said that at once. So that's a symmetric matrix, and how do I, now we might as well pick up some matrix notation. How do I express the fact that this is a symmetric matrix? In simple matrix notation, I would say that K is the same as K transpose. The transpose, everybody knows, it comes from, oh, I shouldn't say this, flipping it across the diagonal. That's not a very math thing to do, but that's the way to visualize it. And let me use a capital T for transpose. Okay, so it's symmetric. Very important, very, very important. That's the most important class of matrices, symmetric matrices. We'll see them all the time because they come from equilibrium problems. They come from all sorts of, they come everywhere in applications. And we will be doing applications. The first week or week and a half, you'll see pretty much discussion of matrices and the reasons, what their meaning is. And then we'll get to physical applications, mechanics and more. Okay. All right. Now I'm looking for properties, other properties of that matrix. Let me write 2 here so that you got a spot to put it. What are you going to tell me next about that matrix? Well, okay. Actually, that's a good question. Let me write periodic down here. You're using that word because somehow that pattern is suggesting something. But you'll see I have a little more to add before I would use the word periodic. So that's great to see that here. What else? Somebody else was going to say something. Please, please. Sparse. Oh, very good. Sparse. That's also an obvious, a property that you see from looking at the matrix. What does sparse mean? Mostly zeros. Oh, well, that isn't mostly zeros, I guess. I mean, that's got what? Out of 16 entries, it's got 6 zeros. That doesn't sound like sparse. But when I grow the matrix, because this is just a 4 by 4, I would even call this one K4. When the matrix grows to 100 by 100, then you really see it as sparse. So if that matrix was 100 by 100, how many non-zeros would it have? So if n is 100, then the number of non-zeros, wow, that's the first MATLAB command I've written. A number of non-zeros of k would be, anybody know what it would be? I'm just asking you to to go up to 5 by 5. What's the, I mean, you know, I'm asking you to keep that pattern alive. 2's on the diagonal, minus 1's above and below. So, yeah, so 298 would it be? 100 diagonal entries, 99 and 99, maybe 298. 298 out of 100 by 100 would be what? It's been a long summer. Yeah, there are a lot of zeros. Lot, right? Because the matrix has got what, 100 by 100, 10,000 entries out of 10,000. So that's sparse. But we see those all the time, and fortunately we do. Because, of course, this matrix, or even 100 by 100, we could deal with if it was dense. But 10,000, 100,000, order 1 million, which happens all the time now in scientific computation. A million by a million dense matrix is not a nice thing to think about. 1 million by a million matrix like this is a cinch. Okay, so sparse. What else do you want to say? Toplets. Holy Moses. Exactly right. So, but I want to say, before I use that word, so that'll be my second MATLAB command. Thanks. Toplets. What's that mean? What does it? So this matrix has a property that we see right away, which is, or tell me some. Yeah, I want to stay with toplets, but just everybody tell me something more about properties of that matrix. Tridiagonal. Tridiagonal. So that's almost a special subcase of sparse. It has just 3 diagonals. Tridiagonal matrices are truly important. They come in all the time. We'll see that they come from second-order differential equations, which are, thanks to Newton, the big ones. Okay, now it's more than tridiagonal, and what more? So what further? We're getting deeper now. What patterns do you see? What patterns do you see beyond just tridiagonal? Because tridiagonal would allow any numbers there, but those are not. There's more of a pattern than just 3 diagonals. What is it? Those diagonals are constant. If I run down those 3 diagonals, I see the same number, 2's, -1's, and that's what the word tuplets means. Tuplets is constant diagonal. Okay, and that kind of matrix is so important. It corresponds. If we were in EE, I would use the words time invariant filter, linear time invariant. So it's linear because we're dealing with a matrix. And it's time invariant, shift invariant. I just use all these equivalent words to mean that we're seeing the same thing row by row, except, of course, at, shall I call that the boundary? That's like the end of the system, and this is like the other end. And there it's chopped off. But if it was 10 by 10, I would see that row 8 times. 100 by 100, I'd see it 98 times. So it's constant diagonals, and the guy who first studied that was tuplets. And we wouldn't need that great historical information, except that MATLAB created a command to create that matrix. MATLAB is all set to create tuplets matrices. Yeah, so I'll have to put what MATLAB would put. I realized I'm already using the word MATLAB. I think the MATLAB language is really convenient to talk about linear algebra. And how many know MATLAB or have used it? Yeah. Well, you know it better than I. I talk a good line with MATLAB, but the code never runs. Never. And I always forget some stupid semicolon, and you may have had that experience. And I just want to say now that there are other languages, and if you want to do homeworks and want to do your own work in other languages, that makes sense. So people tell me, so the older established alternatives were Mathematica and Maple, and those two have symbolic, they can deal with algebra as well as numbers. But there are newer languages. I don't know if you know them. I just know my friends say, yes, they're terrific. Python is one. Anybody had, okay. And R, I've just had an email saying, tell your class about R, and others. Okay. So, but we'll use MATLAB language because that's really a good common language. Okay. So what is a Toeplitz matrix? A Toeplitz matrix is one with constant diagonals. You could use the word time invariant, linear time invariant filter. And to create K, this is an 18085 command. It's just set up for us. If I can create K by telling the system the first row, 2, -1, 0, 0. That would then, if it wasn't symmetric, I would have to give the first column also. Toeplitz would be constant diagonal. It doesn't have to be symmetric. But if it's symmetric, then the first row and first column are the same vector, so I just have to give that vector. Okay, so that's the quickest way to create K. And of course, if it was bigger, then I would, rather than writing 100 zeros, I could put zeros of 98. 98 and 1. Wouldn't I have to say that? Nor is it 1 and 98. You see why it doesn't run. One row. Well, I guess I'm thinking of that as a row. Maybe I don't know. Anyway. I realize getting this videotape means I'm supposed to get things right. Usually it's like get it right later. But anyway, that might work. Okay. Okay. So there's a command that you know, zeros, that creates a matrix of this size with all zeros. Okay. That would create the 100 by 100 Toeplitz matrix. Good. Okay. Oh, by the way, as long as we're speaking about computation, I've got to say something more. We said that the matrix is sparse, and this 100 by 100 matrix is certainly sparse. But if I create it this way, I've created all those zeros. And if I ask MATLAB to work with that matrix, square it or whatever, it would carry all those zeros and do all those zero computations. In other words, it would treat K like a dense matrix, and it wouldn't know the zeros were there until it looked. But so I just want to say that if you have really big systems, sparse MATLAB is the way to go, because sparse MATLAB keeps track only of the non-zeros. So it knows, and their locations, of course, what the numbers are and their locations. So I could create a sparse matrix out of that, like KS for K sparse. I think if I just did sparse of K, that would create a sparse matrix, and then if I do stuff to it, MATLAB would automatically know those zeros were there and not spend its time multiplying by 0. But of course, this isn't perfect because I've created the big matrix before sparsifying it, and better to have created it in the first place as a sparse matrix. Okay. Now, so those were properties that you could see. Now I'm looking for a little deeper. What's the first question I would ask about a matrix if I have to solve a system of equations, say K, U equal F or something? I've got a 4 by 4 matrix, four what would I want to know next? Is it invertible? Is the matrix invertible? And that's an important question. And how do you recognize an invertible matrix? So this one is invertible. So let me say K is invertible. And what does that mean? That means that there's another matrix, K inverse, such that K times K inverse is the identity matrix. The identity matrix in MATLAB would be I of n, and it's the matrix, the diagonal matrix of ones. It's the unit matrix. It's the matrix that doesn't do anything to a vector. So this K has an inverse. But how do you know? How can you recognize that a matrix is invertible? Because obviously that's a critical question. And many, since our matrices are not, a random matrix would be invertible, for sure. But our matrices have patterns. They're created out of a problem. And the question of whether that matrix is invertible is fundamental. I mean, finite elements has these modes, zero energy modes that you have to watch out for, because what are they? They produce non-invertible stiffness matrix. Okay, so how did we know, or how could we know, that this K is invertible? Somebody said invertible, and I wrote it down. Yeah. Well, okay. Now I get to make a speech about determinants. Don't deal with them. Don't touch determinants. I mean, this particular 4x4 happens to have a nice determinant. I think it's 5. But if it was 100 by 100, how would we show that the matrix was invertible? And what I mean by this is the whole family is invertible. All sizes are invertible. Kn is invertible for every n, not just this particular guy, whose determinant we could take. But as 5 by 5, 6 by 6, we would be up in the... But you're completely right. The determinant is a test. All right. But I guess I'm saying that it's not the test that I would use. Well, so what would I do? I would row reduce. That's the standard, the default option in linear algebra. If you don't know what to do with a matrix, if you want to see what's going on, row reduce. What does that mean? That means, shall I try it? So let me just start it. Just so I'm not using a word that, oops. I'm not using a word that we don't need. Okay. And actually, maybe the third lecture, maybe next Monday, we'll come back to row reduce. Okay. So I won't make heavy weather of that. Certainly not now. Okay, so what is row reduce? So just so you know. I want to get that -1 to be a 0. I'm aiming for a triangular matrix. I want to clean out below the diagonal. Because if my matrix is triangular, then I can see immediately everything. Right? If I reach ultimately I'll reach a matrix U that'll be upper triangular. And that first row won't change, but the second row will change. And what does it change to? How do I clean out, get a 0 in that where the -1 is right now? Okay. Well, I want to use the first row, the first equation, I want to add some multiple of the first row to the second row. And what should that multiple be? I want to multiply that row by something, and I'll say add today. Later I'll say subtract. But what shall I do? Just tell me what the heck to do. I want that. I've got that row, and I want to use it. I I want to take a combination of these two rows, this row and some multiple of this one, that'll produce a 0. So this is called the pivot. That's the first pivot, P-I-V-O-T, pivot. And then that's the pivot row. And what do? Tell me what to do. Add half this row to this one. When I add half of that row to that one, what do I get? I get that 0. What do I get here for the second pivot? What is it? 1.5, 3 halves. Because half of that is, so 3 halves, and the rest won't change. Okay. And now these zeros are, so I'm happy with that 0. Now I've got a couple more entries below that first pivot, but they're already 0. That's where the sparseness pays off. The tridiagonal really pays off. So those zeros say the first column is finished. So I'm ready to go on to the second column. It's like I'm got to this smaller problem with a 3 halves here and a 0 there. What do I do now? There's the second pivot, 3 halves. Below it is a non-zero. I got to get rid of it. What do I multiply by now? 2/3. 2/3 of that new second row added to the third row will clean out the third row. This was already cleaned out. This is already a 0. But I want to have 2/3 of this row added to this one. So what's my new third row? Starts with 0, and what's the third pivot now? You see the pivots appearing? The third pivot will be 4/3, because I've got 2/3 of this -1, and 2 is 6/3. So I have 6/3, I'm taking 2/3 away, I get 4/3, and that -1 is still there. So you see that this is fast. This is really fast. And the next step, maybe you can see the beautiful patterns that are coming. Do you want to just guess the fourth pivot? 5/4. Good guess. Right. Okay. 5/4. Now, this is actually how MATLAB would find the determinant. It would do elimination. I call that elimination because it eliminated all those numbers below the diagonal and got zeros. Now what's the determinant? If I asked you for the determinant, and I will very rarely use the word determinant, but I guess I'm into it now. So tell me the determinant. 5. Why is that? I guess I did say 5 earlier. But why? How do you know it's 5? How do you know that, whatever the determinant of that matrix is, why is it 5? Because it's a triangular matrix. Triangular matrices, you've got all these zeros. It's there. You can see what's happening. And the determinant of a triangular matrix is just the product down the diagonal. The product of these pivots. The determinant is the product of the pivots. And that's how MATLAB would compute a determinant. And it would take 2 times 3 halves times 4/3 times 5/4, and it would give the answer 5. My friend Alan Edelman told me something yesterday. MATLAB computes in, floating point. So 4/3 is not, that's 1.3333, etc. So MATLAB would not, when it does that multiplication, get a whole number, right? Because in MATLAB, that would be 1.333, and probably it would make that last pivot a decimal, a long decimal. And then when it multiplies that, it gets whatever it gets. But it's not exactly 5, I think. Nevertheless, MATLAB will print the answer 5. It's cheated, actually. It's done that calculation, and I don't know if it takes the nearest integer. When it knows that I shouldn't tell you this. This isn't even interesting. The determinant of an integer matrix, whole numbers, is a whole number. So MATLAB says, better get a whole number. And somehow it gets one. Actually, it doesn't always get the right one. So maybe later I'll know the matrix that whose determinant might not come out right. Okay, but ours is right, 5. Now, where was this going? It got thrown off track by the determinant. What's the real test? Well, so I said there are 2 ways to see that a matrix is invertible or not invertible. Here we're talking about the first way. How do I know that this matrix, I've got an upper triangular matrix. When is it invertible? When is an upper triangular matrix invertible? That's upper triangular is great. When you've got it in that form, you should be able to see stuff. So this key question of invertible, which is not obvious for a typical matrix, is obvious for a triangular matrix. And why? What's the test? Well, we could do the determinant, but we can say it without using that long word. The diagonal is non-zero. K is invertible because the diagonal, no, it's got a full set of pivots. It's got 4 non-zero pivots. That's what it takes. That's what it's going to take to solve systems. So this is the first step in solving the system. In other words, to decide if the matrix is invertible, you just go ahead and use it. You don't stop first necessarily to check invertibility. You go forward, you get to this point, and you see non-zeros there. And then you're practically got to the answer here. I'll leave for another day the final going back upwards that gives you the answer. Okay, so K is invertible. That means full set of pivots, n non-zero pivots. And here they are, 2 3/2, 4/3, and 5/4. Worth knowing because this matrix K is so important. We'll see it over and over again. Part of my purpose today is to give some matrices a name, because we'll see them again, and you'll know them, and you'll recognize them. Now, while I'm on this invertible or not invertible business, I want to ask you to change K, to make it not invertible. Change that matrix. How could I change that matrix? Well, of course, many ways. But I'm interested in another matrix, and this will be among my special matrices. And it will start out the same. It'll have these same diagonals. It'll be tuplets. I'm going to call it C. And I want to say, the reason I'm talking about it now is that it's not going to be invertible. And I want to say what, I want to choose a particular, I want to tell you a C and see if you can tell me why it is not invertible. So here's the difference. I'm going to put -1 in the corners. Still zeros there. So that matrix C is still has that pattern. It's still a tuplets matrix, actually. That would still be the matrix tuplets of 2, -1, 0, -1. I claim that matrix is not invertible, and I claim that we can see that without computing determinants. We can see it without doing elimination, too. MATLAB would see it by doing elimination. We can see it by just human intelligence. Now, why? How do I recognize a matrix that's not invertible? And then by converse, how a matrix that is invertible. I claim, and let me say first, why that letter C. That letter C stands for circulant. It's because this word circulant, why circulant? It's because that diagonal, which only had 3 guys, circled around to the 4th. This diagonal that only had 3 entries circled around to the 4th entry. This diagonal with 2 zeros circled around to the other 2 zeros. The diagonals are not only constant, they loop around. And that's, you use the word periodic. Now for me, that's the periodic matrix. That matrix C, a circulant matrix, comes from a periodic problem because it loops around. It brings numbers, sort of number 0 is the same as number 4 or something. And why is that not invertible? It's the thing is, can you find a vector? Because matrices multiply vectors, that's their whole point. Can you see a vector that it takes to 0? Can you see a solution to CU equals 0? I'm looking for a U with 4 entries so that I get 4 zeros. You see it? All ones. All ones. That will do it. So that's a nice, natural entry, the constant. And you see why we haven't spoken about multiplying matrices. So times vectors. And most people will do it this way, and let's do this one this way. You take row 1 times that, you get 2 minus 1, 0 minus 1, you get the 0 because of that new number. Here we always got 0 from the all ones vector, and now here that minus 1, you see it's just right. If all the rows add to 0, then this vector of all ones will be, I would use the word in the null space if you wanted a fancy word, a linear algebra word. What does that mean? It solves CU equals 0. And why does that show that the matrix isn't invertible? Because that's our point here. I have a solution to CU equals 0. I claim that the existence of such a solution has wiped out the possibility that the matrix is invertible. Because if it was invertible, what would this lead to? If invertible. If C inverse exists, what would I do to that equation that would show me C inverse can't exist? Multiply both sides by C inverse. So you're seeing, just as first day, you're seeing some of the natural steps of linear algebra. Row reduction. Multiply, when you want to see what's happening, multiply both sides by C inverse. That's the same as in ordinary language. Do the same thing to all the equations. If I multiply both sides by the same matrix, and here I would get C inverse CU equals C inverse 0. And what does that tell me? I made it long. I threw in this extra step. You were going to jump immediately to C inverse C is I, is the identity matrix. And when the identity matrix multiplies a vector U, you get U. And on the right side, C inverse, whatever it is, if it existed, times 0 would have to be 0. So this would say that if C inverse exists, then the only solution is U equals 0. That's a good way to recognize invertible matrices. If it is invertible, then the only solution to CU equals 0 is U equals 0. And that wasn't true here. So we conclude C is not invertible. C is therefore not invertible. Now, can I even jump in? But I've got 2 more matrices that I want to tell you about that are also close cousins of K and C. But let me just explain physically a little bit about where these matrices are coming from. So maybe next to K, I'm not going to put periodic there, right? That's the one that I would call periodic. This one is fixed at the ends. Can I draw a little picture that aims to show that? Aims to show where this is coming from. It's coming from, I think of this as controlling like 4 masses, mass 1, mass 2, mass 3, and mass 4, with springs attached and with endpoints fixed. So that would, if I put some weights on those masses, so we'll do this. Masses and springs is what is going to be the very first application. And it will connect to these matrices. And all I'm doing now is just asking to draw the system, draw the mechanical system. Actually, I'll usually draw it vertically. But anyway, it's got 4 masses, and the fact that this -1 here got chopped off, what would I call that end? I'd call that a fixed end. So this is a fixed matrix. Both ends are fixed. And it's the matrix that would govern, and the springs and masses all the same is what tells me that the thing is tuplets. Now, what's the picture that goes with C? What's the picture with C? Do you have an instinct of that? So C is periodic. So again, we got 4 masses connected by springs. But what's up with those masses to make the problem cyclic, periodic, circular, whatever word you like? They're arranged in a ring. The first guy, the 4th guy comes back to the first one. So the 4 masses would be, so in some kind of a ring, the springs would connect them. I don't know if that's suggestive, but I hope so. And what's the point of, can we just speak about mechanics 1 moment? How does that system differ from this fixed system? Here, the whole system can't move, right? If there's no force, then nothing can happen. Here, the whole system can turn. They can all displace the same amount and just turn without any compression of the springs, without any force having to do anything. And that's why the solution that kills this matrix is 1, 1, 1, 1. So 1, 1, 1, 1 would describe a case where all the displacements were equal. In a way, it's like the arbitrary constant in calculus. You're always adding plus C or something. So here we've got a solution of all ones that produces 0. The way the derivative of a constant function is the 0 function. Okay, so this is just like an indication. All right. Now, can I, yes, perfect. I've got 2 more matrices. Are you okay for 2 more? Yes, okay, what are they? They are, okay, a different blackboard for the last 2. So one of them is going to come by freeing up this end. So I'm going to take that support away. And you might imagine a tower, like a tower, oscillating up and down, or you might turn it upside down and like a hanging spring, or rather 4 springs with 4 masses hanging onto them. But this end is fixed, and this is not fixed anymore. This is now free. And can I tell you the matrix, the free fixed matrix? Free fixed will be, because it's the top end that I changed, I'm going to call it T. So all the other guys are going to be the same. But the top one, the top row is the boundary row. Boundary conditions are always the tough part, the tricky part, the key part of a model. And here the natural boundary condition is to have a 1 there. That 2 changed to a 1. That 2 changed to a 1. Okay. Now if I asked you for the properties of that matrix, so that's the third. Shall I do the fourth one? So you have them all, you have the whole picture. The fourth one, well, you can guess. What's the fourth? What am I going to do? Free up the other end. So this guy had one free end, and the other guy has B for both ends. B for both ends are going to be free. So this is free fixed. This will be free free. So that means I have this free end, the usual stuff in the middle, no change. And the last row is what? What am I going to put in the last row? To minus 1, 1. Minus 1, 1. So I've changed the diagonal. There I put a single 1 in because I freed up one end. With B, I freed both ends, and I've got 2 minus 1s. Now, what do you think? So this, we've drawn the free fixed one. And what's your guess? They're all symmetric. That's no accident. They're all tridiagonal. No accident again. Why are they tridiagonal? Physically, they're tridiagonal because that mass is only connected to its 2 neighbors. It's not connected to that mass. That's why we get a 0 in the 2, 4 position, something, because 2 is not connected to 4. So it's tridiagonal. It's not tuplets anymore, right? Tuplets says constant diagonals, and these are not quite constant. I would create K. I would take T equal K if I was going to create this matrix, and then I would say T of 1, 1 equal 1. That command would fix up the first entry.
Professor?
Yeah.
Why does making that a 1 free it up?
Yeah, that's a serious question. Maybe can I hang on till Friday and even maybe next week? Because this is very important. When I said boundary conditions are the key to problems, I'm serious. That if I had to think, okay, what do people come in my office ask about questions, I say right away, what's the boundary condition? Because I know that's where the problem is. And so here we'll see these guys clearly. Fixed and free, very important. So in some way, so free means, but also, let me say 2 more words, I never can resist. So fixed means the displacement is 0. Something was set to 0. The fifth guy, the fifth over here, that fifth column was knocked out. Free means that, in here it could mean that the fifth guy is the same as the fourth. The slope is 0. Fixed is, U is 0. Free is, slope is 0. So here I have a slope of 0 at that end. Here I have it at both ends. So maybe that's a sort of part answer. Okay, now I wanted to get to the difference between these 2 matrices and the main properties. Okay, so what do we see? Symmetric again, tridiagonal again, not quite tuplets, but almost, sort of morally tuplets. But then the key question was invertible or not. Key question was invertible or not, right? And what's your guess on these 2? You think that one's invertible or not? Make a guess. You're allowed to guess in this course. Yes, Yeah, it is. Why is that? Because this thing has still got a support. It's not free to shift forever. It's held in there. So that gives you a hint about this guy. Invertible or not for B? No. And now prove that it's not. Physically, you were saying, well, this free guy with this thing gone now, this is now free. Physically, we're saying the whole thing can move. There's nothing holding it. But now for linear algebra, that's not proper language. You have to say something about that matrix. Maybe tell me something about BU equals 0. What are you going to take for U? Yep. Same U. We're lucky in this course. U equal 1, 1, 1, 1 is the guilty vector many times. Because again, the rows are all adding to 0, and the all ones vector is in the null space. Yeah. Okay. If I could just close with one more word, because it's the most important, two words. Because they're the most important words. They're the words that we're leading to in this chapter. And I'm assuming that for most people they will be new words, but not for all. It's a further property of this matrix. So we've got how many? 4 properties or 5? I'm going to go for one more. And I'm just going to say that name first so you know it's coming. And then I'll say, I can't resist saying a tiny bit about it. Okay. So I'll use a whole blackboard for this name. So I'm going to say that K and T are, here comes, take a breath. I have to make you, positive definite matrices. So if you don't know what that means, I'm happy, right? Because, well, I can tell you one way to recognize a positive definite matrix. And while we're at it, let me tell you about C and B. Those are positive semi-definite. Because they hit 0 somehow. Positive means up there, greater than 0. And what is greater than 0 that we've already seen, and we'll say more? The pivots were. So if I have a symmetric matrix and the pivots are all positive, then that matrix is not only invertible, because I'm in good shape, the determinant isn't 0, I can go backwards and do everything. Those positive numbers are telling me that more than that, the matrix is positive definite. So that's a test. We wouldn't want to, we'll say more about positive definite, but one way to recognize it is compute the pivots by elimination. Are they positive? We'll see that all the eigenvalues are positive. The word positive definite just brings the whole of linear algebra together. It connects to pivots, it connects to eigenvalues, it connects to least squares. It's all over the place. Determinants too. Yeah. Okay, questions or discussion? It's a big class and we're just meeting for the first time, but there's lots of time chance to ask me. I'll always be here after class. So we stop today. I'll see you Friday or this afternoon. If this wasn't familiar, this afternoon would be a good idea.